Hi everyone. So we were talking about graphs last lecture, and today we're going to continue with graphs. I was talking about graph traversals and told you about depth first search and showed you some pseudocode for that. Today we're going to look at breadth first search, which is a little bit more complicated. Breadth first search, we usually just call it BFS for short. Breadth first search is a little bit like a level order tree traversal, but we apply it to a graph instead of a tree. Now, breadth first search, unlike depth first search, is not naturally recursive. It's not easy to write it as a recursive procedure. Instead, we are going to use a queue. So the idea is breadth first search is that we're going to start by choosing an arbitrary vertex, any vertex you like. We're going to visit that vertex first. Then we're going to visit all of the vertices that are at a distance of 1 from that vertex. Then we're going to visit all the vertices at a distance of 2, so you can reach them from the starting vertex by a path of length 2. And then all the vertices a distance of 3 away, and then 4 away, and so on. And here is some pseudocode for that. It's definitely longer than DFS. You probably don't want to copy it all down right now. It'll be in the lecture notes later. But breadth first search takes as input a starting vertex U. And the first thing we do is we visit that vertex U. So the first 2 lines, we're visiting U. Once we've done that, what we're going to do is we're going to create an empty queue, and then we're going to put U, the starting vertex, on that queue. So here's my picture of a queue with U in it and nothing else. Now what we're going to do is we're going to have a loop that keeps visiting neighbors of vertices that we've already visited. So we're going to take U and we're going to check all its neighbors, see if they've been visited yet. If not, we go visit them and put them on the queue. And so this loop is going to keep looping until the queue is empty, and that's only going to happen when we have finished visiting every vertex that we can reach from U. What does the loop do? Well, we're going to dequeue a vertex, and then we're going to check all of the edges that go out from that vertex. So we have another loop, a for loop here, that says, here's a vertex, I want to look at all the edges out. And for each one of those, we need to check whether that neighbor vertex has been visited yet. Very important, we don't want to visit the same vertex twice. If the vertex has not been visited, then we visit it, and then we put it on the queue to make sure that later on we will check out all of its neighbors and make sure that they've all been visited too. So with this code, one thing you'll notice is that I have a visit method that takes a parameter here. When I visit a vertex W, I am passing along the vertex by which I got to W. So what are V and W? There's an edge VW in the graph, and I follow that edge and I find W and I visit it. When I visit W, I'm going to pass in V, the vertex that allowed me to find W. And I'm going to use that information. There are lots of different things you could do with a depth first search routine, but one of them is to do this pseudocode here. So this is a class for vertices, and the idea is that I'm going to store some information with each vertex. Each vertex is going to have a parent reference that points to some other vertex. Which vertex is that? I'm going to have it point to the vertex by which we found this vertex. So the reason why we're visiting the big vertex is because we visited that little vertex previously. I'm going to call that the parent of this vertex. My parent is the vertex by which the breadth first search found my way to me. And I will also record a depth. And the depth is a number which is the distance from the starting vertex to the vertex I'm at now. So if that parent was the starting vertex, then this would be at a depth of 1. And of course, I need a visited flag to make sure that I never visit the same vertex twice. And so when I visit that vertex, I set that flag to true. I have this visit code which sets up these pointers, the parent and the origin pointer. And so I always just set the parent to whatever vertex got passed in as a parameter. And for the depth, there are two cases. If this is the starting vertex, then the origin is null. And that means this is the vertex I'm starting at, visiting first. I assign it a depth of 0. Otherwise, I'm going to assign myself a depth by looking at my parent's depth and adding 1, which is what this line does here. So again, to put that in English, when we traverse an edge, VW, and we discover that W has not been visited, so we visit W. Then the depth of vertex W is set to be equal to the depth of vertex V plus 1. And V becomes the parent of W. So let me show you a graph and do a quick breadth first search on that graph so that you can see what all of this code is accomplishing. So I'm going to go back to the city graph that you've seen before. We're going to do breadth first search on that graph, and we're going to start at Albany. And so I'm going to draw a Q at the bottom that that every city is going to wind up on eventually, and do a breadth first search. So when we start on Albany, the first thing we do is visit it. When I visit a vertex, I'll put a second line around it like that. So Albany's been visited. When we visit it, we set its parent to null. So this is the parent pointer. It doesn't point to anything. And we set its depth to 0. Because it has no parent. And 0 is the distance from the starting vertex, Albany, to Albany. Once we've finished visiting Albany, we're going to put it on the queue as well. And now we start the loop that does the breadth first search. The loop repeatedly takes something off the queue, checks all its neighbors, and visits them if they haven't been visited before. So we immediately start the loop, take Albany off the queue, and visit its neighbors. So it has a neighbor, Kensington, so we go check Kensington out. And Kensington has not been visited yet, so we visit it. And we set its parent to Albany. So Kensington's going to have a parent pointer that points back at Albany. And Kensington's going to have a depth of 1 because its depth is its parent's depth. Albany's depth is 0 plus 1. And we do the same thing from Albany to visit Berkeley. We walk along this edge here. We find Berkeley. We check whether Berkeley has been visited. No, it has not. So we go ahead and visit Berkeley. Kensington's visited. Berkeley's visited. Berkeley also has a parent pointer pointing back at Albany, and Berkeley also has a depth of 1. And when we visit Kensington, we put Kensington on the queue. When we visit Berkeley, we put Berkeley on the queue. So now we have finished processing all of the edges out of Albany. We're done with Albany. We do another iteration of the outer loop, which means we look at the queue is empty. No, so we take something off the head of the queue, Kensington. We're going to now visit all of Kensington's neighbors and see if they've been visited already. Well, from Kensington we can get to Albany, which has already been visited, and we can get to Berkeley, which has already been visited, so we don't do anything. We're done with Kensington, so now we look at the queue again and take Berkeley off the queue, and we're going to look at all the edges coming out of Berkeley. So Berkeley has an edge back to Albany. It's been visited. Berkeley has an edge to Kensington. It's been visited. But Emeryville has not been visited. So we go visit it. Emeryville creates a parent pointer that points back at Berkeley. And Emeryville sets its depth to Berkeley's depth plus 1. That is 2. We're done with that. Oh, we put Emeryville on the queue. Then we look for other edges out of Berkeley. There's an edge from Berkeley to Oakland, so we follow the edge from Berkeley to Oakland, and we check whether Oakland's been visited. Nope, so we're going to do Oakland now. Oakland gets a parent pointer that points back to Berkeley, and Oakland also gets a depth of 2 and goes on the queue. Now we're done with Berkeley. We visited all of its neighbors. We go pick another thing off the queue. Emeryville comes off the queue. We check its neighbors. Has Berkeley been visited? Yes. Has Oakland been visited? Yes. We're done with Emeryville. We take another thing off the queue. We have Oakland, so we check Oakland's neighbors. Emeryville's been visited. Berkeley's been visited. Piedmont has not. So we follow the edge to Piedmont and go visit Piedmont. Piedmont's going to get a parent pointer that points back to Oakland and a depth of 3, Oakland's plus 1. We put Piedmont on the queue. We're done with Oakland. We take Piedmont off the queue, check its neighbor, which has already been visited, so we don't do anything. Now the queue is empty. Breadth first search is done. What have we got? What we have actually is, if you look at just the parent pointers, they form a tree. And this tree will point the way from any city in our graph to get back to the starting vertex, and it will be the shortest way to get back to the starting vertex from any given node in the graph. So if you're at Piedmont and you want to go back to Albany, you follow the parent pointer, you follow the parent pointer, you follow the parent pointer, and that is the shortest route from Piedmont to Albany. So we've built a graph. With breadth first search, we've built a tree. We have built a tree that tells us the shortest path from any vertex in this graph to the starting vertex. And the depth tells you the length of that path. Yes? I'm sorry, a little louder, please? Oh, okay. Right. Other questions? Yes? Why do I take items off the queue before checking if they have children? Well, I'm not sure if this is the answer you're looking for, but I need to get everything off the queue eventually. And so I just take them all off whether they have children or not. But I have a feeling that probably not what you were asking. Yeah, when they're off the queue, you can still store them in a local pointer. So you have a local variable that points at them after you've taken off the queue, and then you can manipulate them from there. Yeah. Other questions? All right, I'm going to just write down what I just said. You can find the shortest path from any vertex to the vertex we started at by following the parent pointers. And so that is one of the things that breadth first search gives you. Another thing it gives you is the lengths of those paths. Because if you think of it as a tree, it is the depth of the node in that tree. And one thing I want to recommend is that, I know this went by fast, and if you didn't follow it completely, it's really a good idea to sit down with the pseudocode and take a piece of paper, draw a graph, draw the program stack so that you're keeping track of, or the local variables, and simulate breadth first search yourself. Go through it line by line as if you were the computer and actually run breadth first search yourself on a sheet of paper so you get a feeling for what the algorithm is doing. And that's the best way to learn to understand breadth first search and depth first search as well. Also, a word about the running time. If you're using an adjacency list, then breadth first search runs in linear time. And when I say linear, I mean v plus e. You have to consider both the number of vertices and the number of edges because you can't know which one is going to be bigger. It is possible to have a graph with no edges at all, in which case v dominates e. It is possible to have a graph with v squared edges, in which case e dominates v. So either one of these two terms, E or V, might be the dominant term. You can't say that one is always big O of the other. You have to put them both in this expression to be correct. Yes? If you run breadth first search in a graph with no edges, it is not going to visit all the vertices. If the graph is not connected, then you're only going to visit the connected component of the starting vertex. That's actually really useful if your goal is to find a connected component in the graph, which is another thing that breadth first search is useful for. You want to know what the connected components are? Start with a vertex, run breadth first search. All the nodes you visit are in the same connected component, and all the nodes you didn't visit aren't. Then you can run breadth first search again on one of the nodes you didn't visit the first time until you find all the connected components one by one. Other questions? Let's see where this big O of V plus E... Oh, question over here. Yeah. Louder, please. Adjacency lists I talked about last Wednesday. They are the data structure that... where you, for each vertex, you store a list of all of the other cities that it's connected to. So the data structure that looks like that. let's take a quick look at that pseudocode and just see where this big O of v plus e time comes out. In this pseudocode, I actually left something out. Before you do this, you either have to set all the visited flags to false, or you have to construct an array of visited flags or something like that. However you do it, you have to come up with a set of visited flags and make sure they're all false before you can run breadth first search. And no matter how you do it, that's going to take big O of v time. It takes big O of v time just to get v flags that are all set to false, because the breadth first search needs that. So that's the reason, that's pretty much the only reason why it takes v time. And what takes e time, on the other hand, is if you look at this inner for loop, when you combine that inner loop with the outer loop, then we're going to basically visit every edge once. Or if it's an undirected graph, maybe we'll visit every edge twice, once for each direction, once for VW and once for WV. But we're going to visit each edge a constant number of times, so the inner loop here, this bit runs e times in a directed graph, or it runs at most 2e times in an undirected graph. So the inner loop is probably usually the most expensive part. If it's a connected graph, it's the most expensive part. And so that's going to run big O of e times. That's the main cost of depth first, or breadth first search. Any questions about that? All right, that's if you're using an adjacency list. What if you're using an adjacency matrix? How fast do you think it, or how slow or fast do you think the algorithm is? V squared, yes. So why is it V squared? Again, this loop here, you need to find all of the edges. And the only way to find all of the edges is to actually, for a vertex V, walk through its entire row of the adjacency matrix and check every entry in the adjacency matrix to see which ones are neighbors and which ones are not. So this actually is going to run v squared times total if you are using an adjacency matrix. So again, an adjacency matrix is probably only appropriate if the number of edges in your graph is close to v squared. Otherwise, this becomes really expensive. Yes? Since you're using the what? If you have a undirected graph, maybe you can use only the upper half of the matrix, but that's still v squared over 2. So if you're only using half the matrix, it's still big O of v squared in the end because the constant factors don't matter. Other questions? All right, so as I said, BFS runs in big O of v plus e time with adjacency list, but it's big O of v squared time with an adjacency matrix. And let me remind you that that's exactly the same as depth first search. Those two running times for those two data structures, same thing, depth first search or breadth first search. Next, I want to talk about a variant of graphs that come up in a lot of algorithms and a lot of applications. We call them weighted graphs, which just means a graph in which every edge has been assigned a numerical weight with some meaning. That's a weight. What was the alternative? A cast? Oh, cost. You know, there are graph algorithms that assign both a weight and a cost to each edge. They usually have different meanings. When you only have one, we usually use the term weight. Weights and costs do have different meanings, but you can have, in principle, any number of numerical quantities assigned to each edge, depending on what your application does and how it interprets those numbers. So each edge in a weighted graph is labeled with a numerical number, which is usually called a weight, but might be called a cost. And that weight might express the distance between two nodes. It might express the amount of capacity that can flow through a pipe going from one location to another. It might reflect the cost of flying from one city to another, any number of things. Now, we have to, when we have a weighted graph, change our data structure a little bit to have somewhere to put these numbers. And how we do that depends on whether we're using an adjacency matrix or an adjacency list. So if you're using an adjacency matrix, typically instead of using an array of Booleans, you would use an array of numbers. It could be an array of ints or doubles or whatever, depending on what numerical type is appropriate for the weights that your application is using. So, you have a matrix. Now it's got numbers in it. Now, you want to have a way to represent edges that are not in the graph. So when we used a Boolean array, we used false to say there's no edge connecting these two nodes. When you're using an array of numbers, you have several choices how to do it. One thing you can do is you can have a special value, which means there's not an edge connecting these two nodes. So for instance, I might use, in some applications, 0 to mean there is no edge connecting node 1 to node 3. But there are other applications where 0 is actually a meaningful weight and does not mean the same thing as no edge. And then maybe you would use integer dot minint, or the smallest possible integer, and hope that nobody ever wants to use that as an actual edge weight. If they do want to use that as an actual edge weight, you can always fall back on having two matrices, a matrix of Booleans that tells you which edges are in the graph, and a matrix of numbers that gives you the weights for the ones that are in the graph. If you have an adjacency list, on the other hand, then remember what we've got is a list of lists. That's what an adjacency list is. And all those little lists, the second level lists, you can, if they're list nodes, you can just add an extra field to those list nodes so that you have room to put that weight. So now each list node will include a weight. One extra field. And just to show you what that means visually, since I just drew this handy-dandy adjacency list, it means that you also add a number here and you add a number here that tells you the weights of the edge connecting Albany to Berkeley, the weight of the edge connecting Albany to Kensington. So it's just one extra field that you store in that list node. So that's pretty much all you need to know about how to store these things. One other thing I'll mention is that if you're storing an adjacency list as an array of arrays instead of a list of linked lists, then now you need two arrays. One array for the destination vertices and one array with the weights, and you need that for every source vertex. So now you have two arrays for every source vertex instead of one. Any questions about these representations, how to represent a weighted graph? Yeah.
Sorry, I'm a bit confused about how the weights of the matrix are mapped to the actual nodes on the graph.
In the adjacency matrix? Okay. So in this matrix here, I'm assuming that these are the destination vertices. And I'm sorry. Usually the source on the is the rows, and the destination is the columns. So, for instance, this box here with the 5 in it means that there is an edge that goes from source vertex 2 to source vertex 3, and that edge has a weight of 5, and I'll usually draw that by writing the number next to the edge in the graph. So does that answer your question, or what's your question? You're welcome. So given that that's how we represent graphs, what are some problems that people care about solving that use weighted graphs? There's several. I will tell you about two, and we'll actually look at an algorithm for one. So one of the classic problems involving weighted graphs is called the shortest path problem. The obvious version of the shortest path problem is you are calling Google Maps and you're asking it to find the shortest driving directions to get you from Berkeley to Los Angeles or something like that. So how does Google Maps does it? Well, it models all these street networks as a graph. There's intersections, which are vertices of the graph, and there are roads, which are edges on the graph, just like the Berkeley street map I showed you last time. And you try to compute the shortest path from your Berkeley source node to your Los Angeles destination node. Each edge of the graph is labeled with times, the rough approximate time it takes to get from one intersection to the next intersection. And so you use that and try to compute the shortest path from the starting point to the end point. Here, shortest means the one that would take the least time. Or it means the one where the sum of the edge weights on the path are smallest. Now, we have already just seen one way to solve a shortest path problem, which is that breadth first search solves this if all the edge weights are 1. And for some applications, that's all you need. But for, say, finding the shortest path on a map, it's not going to work because not every street takes exactly the same amount of time to drive. So when you have different edges taking different amounts of time to drive from one intersection to the next, the algorithm gets more complicated. The most famous algorithm for solving this when the weights are not all 1 is called Dijkstra's shortest path algorithm, and you will learn that algorithm if you take CS 170. A second problem that comes up in the real world a lot is called the minimum spanning tree problem. With the minimum spanning tree, here's an example of where this problem would come up. Suppose that you're wiring a house for electricity, and you have various points in the house where you want to install an outlet. So you've got specific fixed electrical outlets. You also have somewhere in the house a source of electricity, where the electricity is coming through the wall into the basement or whatever. And you want to attach them all together. But you don't have to have a separate wire going from every outlet to the source in the basement, because electricity will go down any old cable. So you can do things like attach one outlet to a different outlet, and then attach that outlet to another outlet, and then attach that outlet to the cable in the basement. As long as all the outlets and the cable in the basement are all connected to each other by the graph, it doesn't matter exactly which route they take. Electricity doesn't care which way it goes through your basement. So we have a graph in which each vertex is either an outlet, there's a bunch of those, or the source of electricity. Usually there's just one of those, but there might be more than one. Every outlet needs to be connected to the source, but not necessarily directly. So what we do is we have a graph that shows all the different ways that we could connect one outlet to another outlet, or one outlet to the source of electricity, and we label the edges of the graph. With the length of wire that is necessary to connect one outlet to the next, or one outlet to the source. And copper wiring is expensive, so maybe we'd like to ask, how can we connect everything together so that there's always one path from any node to any other node in the graph, but we use as little wire as possible? And that is our goal. So maybe the graph looks like this, and so we're looking for a subset of those edges that forms a tree using as little wire as possible. So the goal is to get from this input to this output. We're just selecting a subset of the edges. We're going to have a tree when we're done, because a tree is the minimum number of edges that will connect every node to every other node. So now I'm going to tell you an algorithm for solving this problem. And the algorithm, as with many things in math and computer science, is not invented after the person who invented it first, but is named after the person who invented it maybe third or fourth. So let's go back into our formalism. Our graph, we're going to call it G, which is a set of vertices V and edges E. And it is undirected. This is just a naturally undirected problem. It doesn't really make sense on a directed graph. I want to define what a spanning tree of a graph is. So I'm going to create a spanning tree of G, and I will call that new graph T, and it has the same vertices as G, but a different set of edges, which we'll call F. And what is it? It's a graph, again, with the same vertices as G. And it also has V minus 1 edges, because that's what a tree always has. If you have V vertices connected together in a tree, you have V minus 1 edges connecting them. And those edges have to come from G and form a tree, no loops, no cycles. Exactly one path between any two vertices. So that's what a spanning tree is. I want to mention that for a graph to have a spanning tree, it has to be connected. If the original graph we started with is not connected, then it's not going to have a subgraph that connects all the vertices together either. So we're not going to get a spanning tree. But if you have a graph that's not connected, then you can still get something called a spanning forest. Like if your input looks like this, well, that's not a connected graph, but the algorithm I'm about to show you will still create a spanning forest, which is a set of trees, one tree for each connected component of the input graph. But let's forget about that for now. Let's just assume that G is connected, not like that, and go ahead and find a spanning tree for it. So even unweighted graphs have spanning trees. If the graph is weighted, then some spanning trees are more expensive than others. And we want the least expensive one, which we'll call a minimum spanning tree. Now, I will talk about the total weight of a tree, and when I talk about the weight of a tree, that means that we are summing the weights of all its edges. And so a graph has many spanning trees. We're looking for the one where the sum of all its edge weights is minimal, as small as possible. And there might be more than one of those. Not only are there usually many spanning trees, but sometimes there are multiple minimum spanning trees if you have several edges that have the same weight. So there might be more than one of these. We're just trying to find one minimum spanning tree. If there's more than one, great, we'll settle for any one. So now let me actually give you Kruskal's algorithm in 4 steps. Well, 4.5 steps, depending how you count. We're going to start by creating a new graph. This new graph we create will have exactly the same vertices as our input graph G, but it doesn't have any edges yet. So we're going to start with a graph that has no edges. Then we're going to add edges one by one until we have a tree. Now we need to decide which edges to add from G and which edges not to add. To figure that out, we're going to take all the edges, we're going to make a big list of all the edges in G, and we're going to sort them by weight. So, second step is make a list of all the edges in G. We have an adjacency list already, or an adjacency matrix, but neither of those is a convenient format. We just want to have one single list, an array, or a linked list with all the edges in it. Then the third step is we're going to sort those edges by weight. And we want to start our list with the least edges and going from that to the edges with the greatest weight. All right, so we've sorted all the edges by weight. Now we're going to go through them one by one, starting from the edge with the least weight, moving up to the edge with the biggest weight. And for each edge, we're going to ask, do I want to add this edge to my minimum spanning tree? And the answer is yes, if it will still be a tree or a forest. No, if it will create a loop or a cycle. So we iterate through the edges in sorted order. From smallest weight to biggest weight. And for each edge in the list, let's call the current edge UW. And now here's the inner loop that makes everything work. For A, we have to check whether or not U and W are already connected by a path. If they're already connected by a path, I don't want to add the edge UW because that will create a loop. I don't want to have a loop, I want to have a tree. But if they're not connected yet, then this is the best way to connect it because it's the least edge that will bring them together. So then we add that edge if they're not already connected. That's it. That's Kruskal's algorithm. And this algorithm, because it never adds UW if some path already connects them, the output T is guaranteed to be a tree. Again, that's assuming that G is connected. If the input is not connected, if the input graph is not a connected graph, then T is guaranteed to be a forest. So what I'm really saying here is that T is guaranteed not to contain a loop or a cycle. We'll never add a cycle. Now what I don't want to do is go through a complete proof of why this algorithm works, but if you are interested in seeing one, Goodrich and Thomasia have one. If you have the 5th edition, it is on page 649, and so that's for those of you interested in understanding why this algorithm works. What I'm going to do instead is demonstrate the algorithm. So here's a graph. All the edge weights are labeled. We're going to go through the edges one by one, and the very first and smallest edge weight is 144, so we add that first. The second smallest is this 184. Are JFK and BWI already connected? No, they're not, so we add that edge. The third smallest edge is this Boston to JFK edge, which has a cost of 187. Are JFK and Boston already connected? No, they're not, so I add the edge. The fourth smallest edge is San Francisco to Los Angeles. They're already connected? No, they're not, so I add this edge. The fifth smallest edge is, where is it? ORD to BWI. Are they already connected? No, they're not, so we add them. The sixth smallest edge is ORD to JFK. And hey, ORD actually is already connected to JFK through BWI. There's a path going from one to the other. So we're not going to add this edge. That edge gets excluded from our minimum spanning tree. Then ORD to Dallas-Fort Worth is number 7, and they are not connected yet, so we connect them. The 8th biggest edge is over here, PVD to ORD, but they are connected. ORD goes to BWI to JFK to PVD, so this edge is not going to make it into the minimum spanning tree. 9th smallest edge is Boston to ORD, and again, they are already connected by a path, so this edge is not going to make it. The 10th edge brings Miami into the graph because Miami is not yet connected to anyone else. The 11th biggest edge, nope, already connected. 12th biggest edge is here, nope, already connected. 13th biggest edge is Los Angeles to Dallas-Fort Worth. That one actually, they're not connected yet, so we add them. At this point, we now have a tree. The algorithm will keep going, perhaps not realizing that it's done, but no further edges can be added because all the vertices are connected to each other now. And just so you know, the overall running time is big O of V plus E log V. That's the worst case running time with an adjacency list. And check out the end of the notes if you want to know why. See you all on Wednesday.